आज इस वीडियो में मैं आपको बताऊंगा सिमेट्रिक और स्क्यू सिमेट्रिक मैट्रिसेस पर बेस्ड मोस्ट इम्पॉर्टेंट क्वेश्चंस और उनके सॉल्यूशंस के बारे में. सो कीप वाचिंग दिस वीडियो टिल द एंड. So this is the most important type of sum which is most frequently asked in the examination based on symmetric and skew-symmetric matrix, and the question is express the following matrix as sum of a symmetric and a skew-symmetric matrix, and this matrix is given. Means we are given a matrix, a square matrix in the examination, and we have to express this matrix as sum of a symmetric and skew-symmetric matrix. And if you don't know what is symmetric and what is a skew-symmetric matrix, please watch my dedicated video on the concepts. So what we have to do in this? First, we let the matrix as A. We denote the matrix by some alphabet like A, B, C. So here we take A. Let A is equal to matrix 4, 3, 2, 1, 4, 6, 7, 2, 8. Then we take the transpose of the matrix. Transpose of the matrix. To find the transpose of the matrix, we interchange the rows and the columns. So first row becomes first column. So we write 4, 3, 2 as column, and the second row as second column 1, 4, 6, and third row as third column 7, 2, 8. Then we find the sum of these two matrices, that is A plus A dash is equal to matrix 4, 3, 2, 1, 4, 6, 7, 2, 8. This is A, and we have to add A dash, so A dash is this. So we write matrix 4, 1, 7, 3, 4, 2, 2, 6, 8. So adding these two matrices, we get 4 plus 4, 8, 3 plus 1, 4, 2 plus 7, 9, 1 plus 3, 4, 4 plus 4, 8, 6 plus 2, 8, 7 plus 2, 9, 2 plus 6, 8, and 8 plus 8, 16. Let it be equation number 1. Then we find the difference of these two. So A minus A dash. So A is 4, 3, 2, 1, 4, 6, 7, 2, 8. 7, 2, 8. Minus A dash. And A dash is 4, 1, 7, 3, 4, 2, 2, 6, 8. 4, 1, 7, 3, 4, 2, 2, 6, 8. Now, take the difference of the corresponding elements. 4 minus 4 is 0. 3 minus 1, 2. 2 minus 7 minus 5. Minus 1 minus 3 minus 2. 4 minus 4, 0. 6 minus 2, 4. 7 minus 2, 5. 2 minus 6 minus 4, and 8 minus 8 is 0. Let it be equation number 2. As we know, the sum of a matrix and its transpose is always a symmetric matrix. And the difference of any square matrix and its transpose is always a skew-symmetric matrix. Now adding equation 1 and 2, we get 2a is equal to, because a dash will be cancelled by minus a dash, and we are left with 2a on the left hand side, and on the right hand side we get 849 488 9 816 plus 0 2 minus 5 minus 2 0 4 5 minus 4 0. Now transposing this 2 to right hand side, it will divide both the terms. So we have A is equal to half matrix 8 4 9 4 8 8 9 8 16 plus half matrix 0 2 minus 5 minus 2 0 4 and 5 minus 4 0. So finally we get A is equal to, because half is a scalar, and if we multiply any matrix by a scalar, it will multiply each and every element. So half will multiply each and every element, means 2 will divide each and every element. So half into 8 4, half into 4 2, half into 9 9 upon 2, 4 into half 2, half into 8 4, half into 8 4, half into 9 9 upon 2, half into 8 4, and half into 16 8. Similarly, in the next second matrix, we have to multiply each and every element by half. So we get 0 1 minus 5 upon 2 minus 1 0 2 5 upon 2 minus 2 and 0. As you see, this is a symmetric matrix. 2 is in front of 2, 9 by 2 is in front of 9 by 2, 4 is in front of 4, and this is skew-symmetric matrix because every diagonal element is 0, and about the diagonal, minus 1 is in front of 1, 5 upon 2 is in front of minus 5 upon 2, and minus 2 is in front of 2. So this is a symmetric matrix, and this is a skew-symmetric matrix. So here we have proved that A can be expressed as the sum of a symmetric and a skew-symmetric matrix. Now we are going to discuss the second important type of question based on symmetric and skew-symmetric matrix, and that is a question where we need to prove something symbolically. That is, there is no given matrix in the question and we have to prove a result. So our second question is, if A and B are symmetric matrices, if A and B are symmetric matrices, prove that AB minus BA is a skew-symmetric matrix. So solution: if A and B are symmetric matrices, then A dash must be equal to A and B dash is equal to B. Let us take the transpose of AB minus BA, that is parenthesis AB minus BA dash is equal to, as we know well, the transpose operation is distributive over every bracket. So if we open up this bracket, this transpose goes on both the terms. So we have AB dash minus BA dash, and we better give the reason. Since A plus B dash is equal to, though it is distributive with plus sign also, but here is negative sign, so we have to write A minus B dash is equal to A dash minus B dash. So using this result, we have written AB minus BA dash is equal to AB dash minus BA dash. Now as we know that AB dash is always equal to B dash into A dash, we may write it as B dash into A dash minus, using again the same result here, we may write it as A dash into B dash. Now from equation number 1, A dash is equal to A and B dash is equal to B, so we may replace A dash by A and B dash by B. Here in this expression we get BA minus AB. Now taking minus common out of these two terms, we get minus bracket AB minus BA. Because taking minus common out of these two terms, the sign of the terms will change. This becomes positive and this becomes negative. So we have written AB positive first and then minus BA second. So we come to the conclusion AB minus BA dash is exactly equal to negative of itself. AB minus BA dash is equal to minus AB minus BA. So the transpose of AB minus BA is equal to negative of itself, which is the property of a skew-symmetric matrix. So it implies that AB minus BA is a skew-symmetric matrix. Now we have taken the third important question, which is also a language problem. So what is this? We have to prove two conditions. The first is B dash AB is a symmetric matrix if A is a symmetric matrix. And the second is B dash AB is a skew-symmetric matrix if A is a skew-symmetric matrix. That means being symmetric and skew-symmetric of B dash AB depends on matrix A. If A is symmetric, then B dash AB is symmetric, and if A is skew-symmetric, then B dash AB is a skew-symmetric matrix. So first we have to prove the first part. If A is a symmetric matrix, then A dash is equal to A. Let it be first. Now B dash AB. Now we have to take the transpose of B dash AB. Now we have to consider B as one matrix and the product of AB as the second matrix. So we may apply the property AB dash is equal to B dash into A dash. If we take the transpose of the product of two matrices, that will be equal to the product of the transpose of the second multiplied by the transpose of the first. So using this property, this is equal to the transpose of the second, which is AB, that is AB dash, into the transpose of the first, that is B dash, so B dash dash. Transpose of B dash means double dash, the dash of B dash, because the dash represents the transpose of a matrix. Now, again, using the same property, we may write this as B dash into A dash, and here it is B, because transpose is the matrix itself. So here, if A is a symmetric matrix, A dash is equal to A. So from first, we may replace A dash by A. So we have B dash A B. From first, we have replaced A dash by A here. So we get B dash AB, which is exactly equal to this matrix, which is written inside this parenthesis. So we come to the conclusion that the transpose of this matrix is exactly equal to the matrix itself. So this is the property of a symmetric matrix. So it implies that B dash AB is a symmetric matrix. So we have proved that if A is a symmetric matrix, then B dash AB is also a symmetric matrix. Now we have to prove the second part, and which is B dash AB is a skew-symmetric matrix if A is a skew-symmetric matrix. So proof second. If A is a skew-symmetric matrix, then A dash must be equal to minus A, because this is the property of skew-symmetric matrix, that transpose of the matrix is equal to the negative of itself. So let it be equation number 1. Now we take transpose of B dash A B. So first we have to write B dash, and we have to group AB, that is dash. So inside the bracket we have group A and B together and B dash separated. So we consider this as the first matrix and the product of AB as the second matrix, as we have done in the second part. As we have done in the first part, so since AB dash is equal to B dash into A dash, we have AB dash into B dash dash. Now since AB dash is equal to B dash A dash, again using the same property over here, we have to write B dash into A dash, and here B, because transpose of the transpose is this matrix itself. So now we have to replace A dash by minus A, because from equation number 1 A dash is equal to minus A. So write down B dash into minus A into B, which is simply equal to minus B dash A B. So we see that the transpose of B dash AB is exactly equal to the negative of itself, B dash AB. So this is the property of a skew-symmetric matrix. So we may conclude that B dash AB is a skew-symmetric matrix. So we have proved that B dash AB is a skew-symmetric matrix if A is a skew-symmetric matrix.